Hi, and welcome to module number 47. In the previous module, we started talking about sparse recovery, and I was saying at the time that sparse recovery is a significant topic that we'll start going into in more detail using statistical physics ideas. And we're going to have in this module a discussion of how to move toward optimal sparse recovery. Now, the word optimal, of course, we've discussed it during the optimization part of the course, and it's quite loaded, and we need to think about what type of optimality. And the issue is that the design space for sparse signal recovery is a very complicated design space, a multidimensional design space. And I'm going to explain to you in different ways why it's a complicated design space. And I was thinking about this problem around 2006. And at that time, my colleague and I, Sriram Sarvatam, we were spending many, many days debating for hours different aspects of this design space, what's good, what's not good, what's a realistic assumption, what's not realistic. And in order to design the best, in quotation marks, sparse recovery system, we need to know what we're looking at. Best in terms of what criteria. So one question is, what type of signal do we have? There are different models for different types of signals. One model would be a deterministic model. A deterministic model is something that pure mathematicians and applied mathematicians like. That is a model where your results must account for all possible signals within a class. So the class may be narrow, but within that class, you need to account for everything. A somewhat different approach is a random approach, where you have a probabilistic class of signals. Some of them will be more likely than others. So some signals will be very likely, others will be not so likely. So that's different from deterministic. It doesn't need to have the same result all the time. It can be, maybe it'll outperform for the common cases, underperform for the slightly less common ones. So it can be, different types of expectations are required. Another consideration is the signal strictly sparse? So by strictly, we mean that most entries would be exactly zero. And recall that when we've been discussing these illustrations of a column vector X, where we have a small number of blue boxes and the rest are white, I've typically been saying that the rest of the entries are going to be small, close to zero. But strictly sparse would mean that they're exactly zero. And let's face it, that's not so realistic in applications. On the other hand, if we make the strictly sparse assumption, it'll be easier to prove things. So are we more interested in proving things, or are we more interested in being closer to applications? Another type of signal, which is called compressible, that's a signal where the sorted entries have some rate of decay. So what I mean is that imagine that this would be initially your signal. Okay, so a few large coefficients and many tiny coefficients. And then when you sort this, and you sort this by magnitude, so let me draw it again, like no need for arrows here. So I'll do this in red, the big guy has the biggest magnitude, and these two guys are the next biggest. And suppose that in magnitude 3 is just a bit smaller than number 2. And then, this is number 4, quite a bit smaller. And all the other ones are small. And compressible models say that there's some geometric rate of decay in the magnitudes of these sorted coefficients. Or what if we have a structured signal? A structured signal would mean that maybe it's sparse or compressible with respect to some basis or frame, or maybe there's some type of structure there. Or this is something that I thought about a few years ago, maybe we have a simple structure. A simple structure means that with a small number of bits, you're getting close to the signal x. You're not going to get exactly because x is presumably continuous valued. And for continuous valued signals, to compress them precisely, you need an infinitely large number of bits. But a simple signal would mean that there's some representation with a small number of bits that gets pretty close, close enough. So there are a lot of different types of signals. That's what I'm telling you. And that's part of why the design space for sparse recovery is a very big design space. But it's not just all the different types of signals. It's also what quality of reconstruction do we require? Maybe we require perfect reconstruction always. And by always, I really mean for a class of signals. So this would be a deterministic type of signal assumption. And for that class of signals, we want to always get perfect reconstruction. And this is a very strict requirement. For example, the people that deal with this type of requirement, when I told you in a previous module that L0 recovery requires n+1 measurements with overwhelming probability, they would say overwhelming probability isn't good enough. Even probability 1 is not good enough. You want always. So maybe we want perfect reconstruction for some class of signals, possibly deterministic, with high probability. High might mean 0.99 or higher, but high, sufficiently high probability. This is not as strict as always. So perfect reconstruction. These are both quite strict. But what if instead of perfect reconstruction, let's realize that when we have, let's say, noisy measurements, it'll be very hard to do perfect reconstruction because occasionally we'll just have bad luck with the noise. So maybe a weaker requirement would be that we get the support set perfect. So support set recovery, which we've talked about features, right? Feature selection. If you have a signal that's strictly sparse, but there are other types of signals. What if we have a signal that's not strictly sparse? Maybe squared error is reasonable. Squared error in signal processing is often the standard error metric. But then there are signals where squared error is not so good. So imagine, for example, that you have a signal or you have a reconstruction method that is going to have a lot of small errors. And when you square them, they're kind of meaningless. But imagine that for whatever reason, the small errors, they're bothersome to you in your application. Now, an absolute value error, an L1 error, would mean that these many, many small magnitude errors are being penalized more, and the smaller number of larger errors will not be penalized quite as much as in squared error. So maybe absolute value error is of interest to your application. And we had a paper on that in 2014. Or, so squared error would be squared L2, absolute error would be L1, but worst case error would be L infinity. Maybe you really care about the large errors. You don't ever want your error to be more than 0.3 units, whatever that unit is. So we had another related paper. After we talked about absolute value error, the L1, we talked about L infinity. And the L infinity norm is it picks off the largest magnitude. So this design space for signal reconstruction has a complicated space of possible signals, a complicated space of possible requirements, what do we deliver, how well do we reconstruct, but also a complicated complexity class. Maybe we're willing to consider any algorithm, no matter how slow it is. Or maybe we're requiring polynomial complexity, or maybe we're requiring near linear complexity, maybe just a bit slower than linear. And actually, it turns out that there are algorithms that are sublinear complexity. Now, I know that this seems weird, but let me explain just a bit what I mean. So by sublinear complexity, imagine that my signal x is of length n, but imagine that the sparsity, the L0 norm in x is k, and k is much, much smaller than n, and we're multiplying x by some matrix, phi, And maybe there's a bit of noise or maybe not. There are different ways, there are different models for this. And these perhaps noisy measurements are denoted by y. So y equals phi x perhaps plus noise n. And there happen to be, for strictly sparse signals, there exist algorithms whose complexity is theta of k times perhaps polynomial of logarithm of n. So if you think about it, k is much, much smaller than n. Imagine, and I'm going to add more space in my text box, imagine n is 1,000,000 and k is 100. So if the polylog n is, let's say, 20, suppose, then 20 times k is 2,000. And 2,000 is much less than 1,000,000, which is equal to n. So there are situations where we have algorithms that they're sublinear in n, but superlinear in k. So again, this design space is very complicated. We need to think about the signal. We need to think about how well do we reconstruct. We need to think about the complexity class for the algorithm. We may not allow these complicated algorithms. And finally, how to account for various imprecisions. There might be measurement noise. There may be an incalibrated matrix, meaning that, let's say, the error in the matrix multiplied by x will feed into every single measurement, and so on. So there are a lot of possible imprecisions, and we want something that's robust. So within this complicated design space, we're searching for something optimal. We're searching for the best, and different people will have different requirements within this design space. And what I'm really saying is there's no single best algorithm. There are directions that lead to good designs. There are approaches to think about the problem that increase the likelihood that you'll do well given your constraints. There's awareness of where you are in the design space. And once you're aware, you're much more likely to choose to select a good algorithm and or to design a new one that meets your needs. So that'll be all for this module.